So we're in the middle of discussing what the textiles and architecture have in common, and I'm extremely happy to welcome now Maria Smigielska. She's an architect and researcher, educated in Switzerland and Poland. She is now based in Zürich. Currently, she's working at Digital Building Technologies of the ETH Zürich, and she was also, and is again, affiliated at the Basel Academy of Art and Design. So her interest lies in technologies, in textiles, and in architecture. And well, she has quite a few projects dealing with these topics. So I warmly would like to welcome you, and I'm very curious about your talk now, which kind of links the textile world to the architecture world. And the last point of the program will be a discussion about how to interconnect architecture and textile design. So the stage is yours. Thank you for being here, Maria.
Thank you. Welcome. Thank you for this nice introduction. I'm happy to present this lecture to you, and very curious about your feedback afterwards and the discussions. So my background is in architecture. I'm an educated architect. However, my interest in digital technologies started already years ago. That's why I came to Switzerland to extend my education. And since then, I'm involved in research as well as teaching. Sometimes also practice, architectural practice, when the need to support architectural offices or individual architects or even creatives with some, let's say, digital tools or softwares that could help their design. But as an architect, I think synthetically. We just had a discussion about it during the workshop, and I kind of see architecture as a synthetic discipline, and that's what I also try to convey in my research, which circulates very much around digital crafts. So I always try to combine material, fabrication, and design as something that is inseparable, and which can communicate with one another through digital infrastructures. That's why I see a huge potential in digital technologies. I am especially interested in how digital technologies can bring new values, aesthetics, and qualities to architecture. And I have been working with multiple fabrication, let's say, digital fabrication technologies, like, for example, metal bending, specifically looking at how we can encode digitally human knowledge about this material. As we know, it's exactly like with maybe textile or rattan. This material, while during deformation, doesn't behave linearly. And the question is, how do we encode that knowledge? How we can actually take that knowledge and really include it in the digital model. Second project, which was an Inter-Swiss project between Erne and HGK in Basel. We were working with wood facades, and we tried to again encode traditional wooden facades and expand their, let's say, aesthetic quality through digital technologies, specifically to robot fabrication and assembly. My recent project is focused on clay, yet another material, having particular properties which are very, very interesting for me, because it's a very traditional material, it's very tactile, it requires a lot of knowledge in hands, and my curiosity is what happens if you actually combine it with a 3D printer. So those are the topics that interest me at large in my research and my work. And I will try to, in this talk, in this lecture, identify or address those questions in digital fabrication combined with with textiles. So just a very brief introduction, digital fabrication and architecture. About subtractive methods, maybe we wouldn't necessarily speak so much over here, but I think additive manufacturing as well as robotic manipulation are of high interest currently, and also high interest in architecture and other disciplines. Specifically, robotic manipulation, this is something that I am very much involved in my work. Robotic arms or industrial robots became, I'm sorry, but it's very sensitive, this keyboard. Industrial robots became more available at the early 2000s when their price dropped significantly down, and instantly creatives, architects, designers saw a potential in that. Originally, this machine was designed to perform repetitive tasks. It comes from automotive industry. However, with a little bit of tweaking, with new software that allows, let's say, architects connect or communicate with the machine, it is actually possible to do very non-standard things. The beauty of this machine is that it's generic. So whatever tool we attach to it, then this task we can perform. That's why you maybe have seen even sewing machines which are hanging on the robotic arm. You probably saw robotic arms with a saw, with other tools to process wood, to process metal, to deform, to fold, to weave. That's why I would like to address this particular machine in textiles, because there is a lot of processes which actually could be extended or expanded in textile industry. In general, textiles in construction are most commonly used as lightweight constructions. You probably know that. These are tents and shelters, and those are actually very primordial, very old architectural structures, probably first ones that we have ever built. They are also mobile and temporary constructions, membrane structures, weather protection membranes, and facade structures. However, through the use of new digital technologies for fabrication as well as new materials, there are new opportunities that emerge, and those I would like to talk about. When we speak about need tectonics, I would like to talk about the project of Mariana Popescu, who currently is an assistant professor at TU Delft and formerly conducted her PhD research at ETH Zürich. She investigated needed flexible formwork for concrete structures as her PhD, and this is one of her research demonstrators. So the beauty of this project is that those types of non-conventional, doubly curved surfaces are extremely hard to be produced in architecture. Normally they require a lot of formwork that allows us to actually construct those shapes. With her, let's say, knowledge and investigation in how to actually take the digital model of such a shape, translate it into knitting pattern, actually knitting it on a very typical knitting machine, and then combine it with different materials like cement and concrete. This is a total game changer when we talk about formwork-less concrete shells. This project is, yes, so this project basically, in her solution, we have no material waste. The structure is very lightweight, so the knitted part is only 25 kilograms of fabric, and it's very also fast to produce because it only took 36 hours of knitting. So just to tell you that in the context of architectural production, this is no time. This is basically no time. Besides, of course, those benefits, which are very practical, this solution, moreover, is highly aesthetic by introducing color, reintroducing color to architecture as part of architectural expression. The software that she has developed rationalizes the given geometry, as I mentioned before, produces the file for production on a standard knitting machine. I can't really tell, and I also don't want to count, but there are multiples parts, knitted parts, which has been produced. Each is unique. And of course, there is a lot of research and collaboration involved in this research project. So not only she investigated yarns, which needs to be very specific, knitting patterns that provide enough strength and little deformation under the load of the concrete. There is also a question of right concrete mixture. So she has collaborated with other PhD researcher who at ETH has been developing a very particular type of concrete that could be sprayed. So this was quite a collaborative project in that sense. There are also some additional supports of falsework elements and tension cables, but overall, this is an extremely sophisticated construction which is done relatively simply. And following the path of knit tectonics, I would like to mention also another project which is more related to biomaterials, specifically mycelium. So there has been a lot of research towards biomaterials happening recently in architecture and design. Mycelium has been successfully tested for bulky elements, so for bricks or panels. And in this particular research, led by Elise Elsaker at the Newcastle University, basically they tried to look into alternatives. So again, we are talking about larger architectural structure that is maybe less bulky, that is a bit more sophisticated in shape. And what they managed to actually obtain is 2 by 2 meters diameter structure with grown mycelium that is strong enough to carry its own weight and be a freestanding vault. So this is, again, architecturally speaking, quite a milestone because it doesn't necessarily need any formwork. It doesn't need steel bars that support the structure. It's a vault that is basically carrying its own weight. And that opens up enormous amount of possibilities how mycelium and knitted formwork can cooperate together in order to create not only shells but also parts of architectural elements like walls, maybe parts of ceiling, or other elements. On the other hand side, I would also not only focus. I would like not to focus only on textiles as a finished product. I think very much about textile is, let's say, in its lower resolution, meaning yards or threads or filaments. Or even strands. That's why the next 2 chapters that I will be talking about is about winding and weaving, which I think those are another areas which are very interesting to look at when we speak about architecture and textiles. So the project of Maria Jablonina from University of Toronto, formerly she was in Stuttgart at the Department of ICD. She herself has built those mobile robots which are able to carry the thread. They are able to transport the thread, wind it on protruding elements like nails, and then go somewhere else and create some larger structures out of it. She's currently an assistant professor at Toronto, and she continues developing this technology. But her research really started as almost do-it-yourself mobile robot with simple mechanism that basically turns around a nail and make a little knot. Those robots can work individually or in teams. Over here we have an example of 2 robots collaborating and walking on 2 different walls. She, of course, has developed, she has implemented, let's say, this particular technology to several thread-based design projects. The robots can, as you can see, travel on various surfaces like walls or floors or even dedicated rails. Some of those projects are more artistic explorations like a sleeping cocoon, but there are also more applied purposes, like for example, this purple reconfigurable partition wall that can be winded, unwinded, and rewinded, depending on what kind of spatial configuration we would like to obtain in our space or office. So depending on what kind of transparency, privacy, insulation, or acoustic we would like to obtain, then we can basically reconfigure those threads on the go without any material waste. This is quite a relatively simple two-dimensional system that takes only 45 minutes to wind. There are also more complex systems over here, which of course then require more complex weaving patterns and filament joints, but I think it speaks for itself in its own way. Continuing the topic of discrete robots, I would like to draw your attention to this project of Fiberbots, which was conducted at Mediated Matter Group at MIT in 2016. It is using robotic agents designed to wind fiberglass around themselves to create strong tubular structures. And in this project, 16 robots independently have built 4.5 meter tall structure in just 12 hours. Those robots can communicate with one another in order to avoid collisions. And also the system can include more of the robots. So we can basically either reduce their amount or we can use 40 or 50 of them if needed. The robot design is, of course, of custom design and operate in particular order. So it inflates, it turns on the UV light, it winds the thread, deflate, and then drive up to repeat the process and just like grow vertically. There are, as mentioned, as depicted here on that slide, there are multiple patterns available for the winding, and as such, those patterns also guide the geometry towards certain curvatures, if the design, of course, intent is such. The next project that I would like to talk about has been conducted since 2012. It's a huge and rich body of work at ICD Stuttgart. This is a research project on lightweight fiber structures. It utilizes carbon fiber, glass fiber, and since recently also flax fibers for a more sustainable approach. Those are some videos from the production of a recent project. But since 2012, during those recent years, they have developed multiple fabrication setups, starting from the top left, one robotic arm and a rotary platform that would wind two types of fibers on the wood ribs. The second one, for example, is the shape of this pavilion is actually driven by the robotic reachability limitation, because when the robot moves its arm, basically it creates a shape of a half sphere. Therefore, this is why they basically just try to expand as much as possible the reach of the robotic arm. So over here, the robot would glue the fibers on the inside of the inflatable structure, and after the fibers would dry, this inflatable structure would be removed. In the third fabrication setup, we have two robots which are collaboratively winding a discrete component in the factory, in the lab. Such components can be really, really large, depending, of course, on the load that the robot can carry. They can be up to 3 meters or even larger. And the most complex, let's say, fabrication configuration number 4, bottom left, would involve a drone that is actually transporting a thread from between two robotic arms, which are placed at a distance. And why such a distance? The goal of this project was to build like a large cantilever, and this is quite impressive. It's 12 meters, and this 12 meters is actually not because of material limitations, but because of the transportation limitations. They just couldn't get a larger truck. Those are quite some milestones, and the use of fibers over here is also quite impressive. The combination of how those two types of fibers are working together. So, for example, carbon fibers are much stiffer, they are much more rigid, they are much more structural than glass fiber. Therefore, as you can see on some of those images, they basically follow certain placement which comes from structural analysis and tells us, okay, over here we have a lot of tension. That's why let's put more of those fibers in that particular location. So those technologies are extremely high tech, as opposed to the former project of Maria Jabłonina, who was actually working at this department. She built her own do-it-yourself robots. Over here, we are talking about something that is extremely interdisciplinary. On board, they had roboticists, architects, engineers, even biologists, because very much those structures are inspired by biological forms. So huge interdisciplinary team of researchers, and there is also a lot of, let's say, communication involved, not only between the machines but also between the machines and actual fabrication setup, because the robots need to know not to pull too much and also need to pull strong enough so that the threads are actually not sagging, but they are also not torn. Therefore, there is a lot of engineering behind those structures. Over here, those are all the resulting projects, which vary not only in those fabrication methods that I mentioned before, but also in the scale, morphology, and scalability. Some of them are fabricated as one piece, as a pavilion that is one of a kind, but some of them are also composed of individual components which can be propagated. Some are even modular, like the project from 2021, which was exhibited at Venice Architecture Biennale. And the project represents a future habitat which is very lightweight as a response to the material scarcities which we are dealing with right now. On the other hand, because they are built from very very robust materials, they are also strong and can be habitable. And speaking of the weight, compared to Le Corbusier Maison Domino, which is a roll building or habitat from the 20th century architecture, the weight footprint of Maison fiber is reduced 50 times. In all those projects, fiber winding responds to the structural conditions of given geometries. So I mentioned carbon fibers are extremely stiff, lightweight, resistant to chemicals and temperatures. They perform much better. Therefore, their placement is, of course, informed by the structural property of the particular geometry. Taking a step further towards weaving, so we are not working. So I'm not going to be talking about threads anymore, but a bit more robust materials, like for example willow. The technique of weaving has been widely acknowledged as one of the most ancient, most ancient craft. The oldest known woven baskets are dated to up to, I think, 12,000 years. In architecture, weaving was first described by Gottfried Semper, which you also mentioned in one of your introduction, in his book, The Four Elements of Architecture. And over there, he describes walls as the one that are made out of wood pieces, branches, plants of varied sizes, which are intertwined in order to form a supportive structure. In some cases, they can also be covered with mud or leaves for a better thermal insulation. And since then, weaving in architecture has been propagated in multiple ways. One way is, let's say, more logical or structural, where we are actually trying to follow the interweaving of different threads or beams or parts. But we also have the aesthetic, let's say, mimicry over here, which is a bit more following the aesthetics of it, which works more like a facade or something that is more an envelope or a decoration. And currently we observe the increased interest in those weaving techniques, especially combined with digital fabrication technologies, for several reasons. Well, first of all, weaving materials are really truly digital as they allow for creation of complex shapes, and as you might know, all the digitalization is actually about opening up design space and introducing diverse geometries. And traditional weaving is also a very sustainable material, so renewable, very fast growth, at the same time cheap, which gain a lot of performance upgrade through actually interweaving. Therefore, it's actually like a free improvement for a very cheap and not very structural material. Integration of the weaving though brings several challenges, and I would like to point them out over here. So the question number one: how can computational tools inform traditional weaving techniques towards novel architectural systems? The second question would be: how can we accurately compute complex behavior of weaving patterns? And three, how can we mediate between the high precision of digital fabrication and imperfections inherent to natural materials? And the third point, I would say that it's not only about mediation between digital fabrication, but also about expectations. That's also mentioned over here, that it's expected that certain fabrics need to always be of the same color. The same applies for architecture. So how can we mediate? How can we mediate that? How can we balance those sustainable approaches which are using materials off the ground and at the same time fulfill all those, let's say, regulations and requirements? So very quickly, because I think I'm above the time, so only two projects described over here. Weaving Enclosure, a researcher group from Politecnico di Milano. They have tried to answer the question of how can we actually predict the behavior of bending of rattan. And they have digitally simulated it. Maybe I will directly jump to this diagram. So yes, they have analyzed, they have done plenty of physical tests and then try to encode it, take it back to the digital model in order to be able to be more aware about internal forces that are happening between the rattan as well as the vertical warps. They have, yes? Okay, we have very little time, so maybe I just directly jump to next project, which I think is extremely interesting. It's just 2 years of teaching and research project at the Karlsruhe Institute of Technology, where they have actually built a custom machine that is conducting the weaving. It's not a robotic arm. It's a machine that is three-dimensional CNC machine, which was just adapted to work with willow. And the goal of this research is to construct those three-dimensional objects which work more structurally, and they are not only, let's say, aesthetic or decorative. Those, of course, digital simulations analyses were backed up with physical tests. And what is interesting is that they propose something which is purely digital construction. So there is no material that is wasted. Willow can be either decomposed or reused, the same earth, because they have built a hybrid system of willow that is actually working as a reinforcement for the earth, and earth that is also stabilizing the rattan. Therefore, this hybrid system is fully recyclable, yeah, it's a huge promise for the future of construction, which produces a lot of CO2 emissions and waste. So that's a brief summary. Maybe I stop over here because of lack of time. But I'm very happy to hear your feedback from the textile perspective, because that's my, let's say, technological / architectural perspective. Thank you for your time.
Thank you. So thank you so much. Maybe we can just start. Are there any questions specifically to projects, or shall we just go on? Yes.
The one where the knitwear with this organic shape. Yes. How do they stiffen out the knitwear first, or?
So there are some some bars which basically kind of create certain tension of the structure, and after that there is a layer of cement and concrete which basically stabilizes the whole structure. There was one photograph we can, if you'd like, we can quickly go back to it. Yes. So this is also something. So there are bars to create certain tension in certain areas, especially on edges. And as you can see over here, there are also some pockets because it's a double knit. There are some pockets which can contain balloons, so to further reduce the amount of concrete being used.
No, now I get it. So along the edges, they pull it, and
yes,
then
exactly.
with this pulling
exactly.
it works.
Yes,
Okay,
exactly.
Okay, now I get it.
So as you see, there is no support directly under those edges. Basically, over here it's being tensioned, over here it's being tensioned, and then the textile is being stretched between those. Yeah.
Okay, more technical questions? Yes,
I have a question for the robots who are like winding the thread around the nails.
Okay.
How do they do it? Do they go like back to the floor and then travel on the other side and up the wall again?
So I guess it depends on the application. So over here, for example, it's fairly simple because the robot can only slide on this bar, and this whole bar is going up and down. So this is quite simple. Over here, I guess each robot is just sitting on each wall, and as far as I remember, there is a moment where they kind of take over the thread. So those robots meet, and basically then the thread is being passed on to another robot to actually go on the other side. So I guess it really depends on a particular design intent, and probably for each of those design, the robots might have had certain differentiations or improvements. Yeah. Okay.
Thank you so much, Maria, for this very rich insight. What intrigues me especially is that there is a new aesthetics coming up, besides all these technical innovations and also sustainability based innovations that are at least possible. So there's also a kind of a new aesthetics which arises.